Now today we will talk about the arc length method. Now imagine that we discussed the Newton-Raphson method, but the main problem with the Newton-Raphson method is at the limit points you have a singular stiffness matrix, and if you see softening, since you have a fixed load, loading, you cannot catch the softening of the load deformation curve. So that's why we have a more sophisticated nonlinear analysis method. So first I will talk about the general form of it, form of arc length method. And I will use the shallow truss formulation as an example case. Now, we call that the force is equal to EA over L cubed. Now that's the residual force, Z square W plus 3 over 2 Z W square plus 1 over 2 W cubed plus KSW minus P. Now we can rewrite this equation Now remember that this part of the equation is equal to normal force times Z plus W over L. So the residual force SW is equal to the internal force of the truss multiplied by ZW over L plus KSW will give us the force in the spring minus P. So basically this is our residual force. So this part of the equation represents the internal forces. And this is the external force. Thus, we can write again the above equation in a more general form. FW is equal to internal forces minus the external force. Okay, and let's call this one equation star. And in the Newton-Raphson based methods, this is the equation that we try to minimize, that we say that should be equal to 0. But the problem with this method is this is a fixed external force. Okay, so in the snap through behavior or the snap back behavior, with this equation we cannot catch the softening, the unstable part of the load deformation curve. So because of this reason we do this. So we say that the starting point of arc length methods so we add an additional variable lambda, and this lambda is equal to FIW minus lambda times FE. And again, let's call this equation plus this time. Now this lambda is a scalar quantity. It's called a load level parameter. So with this lambda, we say that the equation plus defines a state of proportional loading. Okay, so we have a proportional loading and we determine the proportion of the applied loading with this parameter. Okay, all right, now we have lambda here as an additional parameter. So how to define, how to calculate this lambda? Okay, now this gives us an additional parameter, so we have more space to play with, but at the same time I need an additional equation to determine the value of this lambda. So the arc length method by Rix aimed to find the intersection of equation with the arc defined by the following. So we have an S, the length of it is defined by the integral ds, and ds will be equal to square root of dw squared plus d lambda squared. We have a parameter f e. So this is actually nothing but the equation of a hypotenuse, and you can just imagine that this is the radius of a circle. Of course you have this parameter, you can play with it so that you'll have a different types of arcs. So let's call this equation as our double star, and this one, this parameter phi, is the scaling factor. Now, writing equation double star in incremental form, we have the following. The arc length is equal to displacement increment plus load scale factor increment, scale factor, and the applied external force squared, and that should be equal to the user defined arc length. Now with this approach we say that thus iteration at a constant arc can be expressed as so delta v0 square plus delta lambda square, lambda 0 square. So this is particular iteration, phi square f external square. Since we kept the arc length constant, that should be equal to the displacement at the nth iteration plus load factor at the nth iteration, phi T square Fe square, and they should all be equal to delta L square. So this gives us an additional constraint equation. So we say that, which gives an additional constraint equation, which is A is equal to delta W squared plus delta lambda squared Phi squared Fe squared minus delta L squared, and this should be equal to 0. So this is our additional constraint equation. Okay. So let's call this double plus. So now we have this equation to solve, and also we have this equation to solve. So I can say that that should be equal to 0, or let me write it in here, should be equal to 0, and this is our equation plus. So we have two equations to solve together. And with this we introduce an additional unknown, and this additional unknown is this lambda. So when equations plus and double plus are examined, there is an additional unknown. Lambda other than the displacement. So we have these coupled equations. So what I do is, in order to solve equations plus and double plus, these are nonlinear equation. Again, we will use truncated Taylor series expansion. Okay, which we know it as Newton-Raphson method. So let's write the first equation, equation plus, in the truncated Newton-Raphson, truncated Taylor series form. So Fn is equal to F0 plus del F over del W, increment in W. Since we have two variables, I have del F over del lambda, increment in lambda. So this gives me F0 is F0. Del F residual divided by del W gives me the tangent stiffness, KT times W, and I have the external force multiplied by del lambda, and that should be equal to 0. So that's our first equation. The second equation is the constraint equation, and we will again use the truncated Taylor series for it. So An is equal to A0 plus 2 times delta W displacement increment multiplied with the variation change in the displacement, plus 2 times delta lambda. We have the phi square and Fe square equal to 0. So we have two equations and displacement plus, so not two equations, we have this equation equal to the number of displacement, and we have one additional constraint equation which will be sufficient to solve the system. So if I represent these equations in matrix form, I have that lambda equal to minus tangent stiffness minus Fe 2 times delta W 2 delta lambda phi square Fe squared inverse multiplied with F0 and A0, and this is our, let's call it equation 3 pluses. Now, in the classical solution, we were only dealing with this KT and the F0, okay? So in the classical Newton-Raphson equation, we were solving this equation. Now in the arc length method, now we have this additional terms, and combining these two solutions, we get the increment in the displacement and the increment in the scale factors. Now, it looks nice, but there are some issues. The first issue is how do you calculate A0 at the beginning of the iteration? That's one thing. The other thing is, now the KT matrix, we know that it's a symmetrical matrix. It's not, and it can be a banded matrix, okay? It's not a full matrix. But if I add the external forces in the column wise and 2W displacement increments as row wise, as you see, I end up with a non-symmetrical and a non-banded matrix. So solving this matrix at every iteration is computationally very inefficient. So let's write this down. So note that the stiffness matrix in equation remains non-singular. That's the good part. Even when KT, the tangent stiffness, is singular. So it still works if you're at the limit point. On the other hand, the stiffness matrix is neither symmetric nor banded. Which brings us some difficulties in the factorization or the solution of the system. It's computationally very inefficient. So we have to find a way to make this approach computationally efficient, and this is what we will be talking about. Now let's take a look at the Crisfield solution to this problem. So the solution of equation 3 plus can be eliminated with the alternative formulation. So we say the iterative displacement is equal to inverse of the tangent stiffness matrix multiplied by the residual force, W0 and lambda, which is equal to minus tangent stiffness inverse the internal force minus lambda times external force. So let's call this one equation 1. So the Newton change in lambda can be represented as new lambda is equal to old lambda plus the iterative change in lambda. Okay, so that's the second equation, and remember that n represents new, O represents old. Now inserting 2 into 1, we have the following. So that the iterative displacement is equal to minus inverse of the tangent stiffness matrix multiplied by the internal force minus old lambda multiplied by Fe minus iterative displacement in lambda multiplied by Fe. So this should be old as well. So rewriting it, Kt inverse is equal to, we have Fi W0 lambda 0. So I should make it F. This is the residual force again. Minus incremental lambda multiplied, iterative lambda, sorry, multiplied by the external force. So let's call this one equation 3. So from now on I will call this one as FO. Okay, so here the incremental displacement, so iterative displacement, is equal to minus Kt inverse multiplied with the residual force plus delta lambda multiplied with Kt inverse times Fe. Okay, so in that case I will call this displacement as delta lambda hat, and this displacement as delta lambda t. So in that case my iterative displacement is equal to, composed of two components. One of them is due to the residual forces plus incremental lambda, and the other one is, remember that this is the full loading, displacement due to full loading multiplied with a chain iterative scale factor. Okay, so let's write the definitions in that equation. Let's call it equation 4. W hat is equal to iterative change in displacements due to residual forces T will be equal to displacements due to fixed load vector Here I'm doing all these formulations for a single degree of freedom system. So the only unknown in equation 4 is the iterative change in the load scale parameter. If lambda is computed, the new incremental displacements will be equal to, so the incremental displacement, that's the new displacement, is equal to incremental old displacement plus the iterative change in displacement, which now I can write it in the following form: delta W0 plus del V hat plus del lambda del V total. And let's call this one equation 5. Now we also know that we have a constraint equation which we have to satisfy, and this constraint equation gives me the following relationship: delta old squared plus delta lambda old squared phi squared multiplied with the external force should be equal to n nu squared plus delta lambda n squared phi squared fe squared, and that should be equal to minus L squared. Let's call this one equation 6. Inserting equation 5 into 6 leads to the following quadratic equation. So we have A1 del lambda squared plus A2 delta lambda plus A3 is equal to 0. And in this quadratic equation, A1 is equal to METU squared plus phi squared fe squared. A2 is equal to 2 times Vt in parentheses delta W0 plus delta W hat plus 2 times delta lambda 0 phi squared fe squared, and finally the A3 is equal to delta W0 plus that W hat squared minus the arc length squared plus delta lambda 0 phi squared and fe squared. So in order to determine the incremental displacement scale factor, we will use the following quadratic equation. So we will do it at every iteration. At every iteration I have to solve this following quadratic equation and determine delta lambda. Now the problem with this is this equation has two roots. So which root to choose is another issue, and we will talk about it. But in this approach, in order to determine this delta lambda, I don't have to solve any or factorize this full matrix. And once I determine the value of this one, I can determine the value of the displacement increment. Because this is known, I calculate this by using the quadratic equation, and I can calculate this one. Once I determine this value, the iterative change in displacement, I can update my incremental displacement. So with this approach, with these iteration, I can converge to the equilibrium point. Now we will talk about the implementation of this method. Okay, now let's discuss the implementation of the arc length method. So these methods are named as follows. So when we have this scaling parameter equal to the 0, we have a spherical arc length. And this p parameter is set to 1, we have cylindrical arc length method. Why is it called like this? Let's go back to our constraint equation. Or where's this ds? Let's go to that equation. This one. This equation. So when we make this phi equal to 0, we only have the displacement squared, and we are basically forming, and we are constraining it to be equal to delta L. We are just forming a circle in one dimension, in 2 dimensions. But if you have the phi, so you have the effect of displacement increments as well as the loading in your calculations. And this type of arc length method is called the cylindrical arc length method. So let's draw a graph so that we will better understand what this arc length method is doing. So this is the curve that we want to trace, and we start from an equilibrium point. Let's say that we have a converged equilibrium point, and I will show it with W0 and lambda times P. P is the applied loading. So let's say that that's the converged point. So this displacement is W0, and the force here is equal to scale factor multiplied by phi. So the starting point is this. Step 1. Calculate incremental tangential predictor. And we will talk about how we calculate that. And let's call them delta W1 and delta lambda 1 times P. So we apply delta lambda 1 times P, and with this load we use the initial displacement, so this is where we are right now. So this distance is delta W1. Okay, so we determine this incremental tangential predictor in such a way that this distance is equal to delta L. This is the arc length that we input. So basically with this arc length, we are defining the following. We are defining an arc. Okay. Now after that we can start the iterations. Now the first iteration. Calculate the residual force and the tangent stiffness matrix using and lambda 1, and in that case lambda 1 is equal to lambda plus delta lambda 1, and W1 is equal to W plus delta W1. So we calculate the residual force and the tangent stiffness matrix. Now the next step is obtain or determine, so these are known values, determine incremental iterative W hat and iterative WT. Okay, now we have a converge point, and we have the predictor solution. This predictor solution will give us this length. So by using delta W1, delta lambda 1, determine A1, A2 and A3 coefficients. Solve the quadratic equation and then choose the correct root for iterative lambda 1. Once you do that, you can determine this delta W2, which is equal to delta W1 plus residual displacement due to the residual forces plus iterative displacement multiplied by Vt. So with this approach, we actually find another point on this curve. We are tracing, moving on this curve, and now this displacement is equal to delta lambda 2 times P and now this displacement is equal to delta W2, and this one will be iterative W1. This point is W1 lambda 1 P, and this point is W2 lambda 2 P. So with this constraint equation, we were actually moving on this curve towards the load deformation. Okay. Now after that, I can determine delta lambda 2 as equal to delta lambda 1 plus del lambda 1. W2 will be equal to W0 plus delta W2, and lambda 2 is equal to lambda 0 plus delta lambda 2. So this will be the end of the first iteration. Now let's work on the second iteration. Now this time again I will calculate residual force and the tangent stiffness, this time using W2 and lambda 2. Okay, so I'm here, I'm using this slope at this point. Okay, then again calculate let's say use the same wording, determine W hat and WT. Now calculate A1, A2, A3 using delta W1, delta lambda 1, and then V hat and del VT. Remember that I didn't use these two in this calculation because I know that these two will give me delta L. Okay, so that's why I'm calculating A1, A2, A3 by using these two parameters and the new iterative displacements. And then it's the same approach. Solve and choose lambda 1 and continue this way. So these are the iterations, but we have now two unanswered questions. So let's take a look at that. So how do I calculate the incremental, the tangential predictor so that I have this line equal to delta L, and this helps me to draw this arc length? That's the question 1. The second question, yes, we have A1, A2, A3, but we have a quadratic equation, and how do we determine the correct root for this quadratic equation so that my solution will converge? So the first thing that we will do is take a look at the predictor solution. So one approach is, we can say that that's delta P is equal to KT inverse delta QE. Okay, so that's the typical solution that we'll do in the Newton incremental iterative solution with the Newton-Raphson method. So multiplying both sides with delta lambda predictor will give me this. Let's use P here. We have been using P all the time, so this is P. Sorry for that. That's plus. So inserting equation plus into constraint equation, and for the simplification I will write it for phi is equal to 0. Then we have delta lambda P as equal to plus or minus delta arc length divided by square root of squared. Okay, and now which one to choose? The approach is choose the one that has the same sign, with the tangent stiffness matrix. So if phi is not equal to 0, what do? We again come here, calculate a1, a2, a3, solve the quadratic equation. Again, we'll have two roots and use the same approach to figure out what delta lambda p is. Okay, now the other issue is how to choose the correct root. So let's take a look at it. So you can look at the literature and find out that there are many papers about it, but I'll just show one approach. So quadratic equations, that's the problem. Let's call them delta lambda 1 and delta lambda 2. One approach is, in order to choose appropriate delta lambda, the projections of these vectors, I'm just writing it for the general multi-degree of freedom case. In that case, W1 on previous corrections can be calculated. Here I'm saying that this one belongs to the first root, this one belongs to the second root. So the projection that gives the largest value gives the closest correction to the previous one. So basically we are calculating the projections, we are calculating the dot product for both cases, and we take the largest one. And the dot product is as follows. We have delta W for the current iteration, okay, the one that we calculate using these increments, plus W multiplied with delta W of the previous iteration, plus phi square delta lambda n of the previous iteration, delta lambda n plus 1 of the current iteration, plus the lambda that we found multiplied by p times p. So that's the dot product. We calculated it for these two couples. Whichever gives us the largest value will be the closest correction to the previous case. Okay, why are we looking for a closest projection? Because let's take a circle So we are at this point, but I'm drawing a line. So we have two roots. So the one that I want to choose is this one, not that one. So that's why I'm looking for the closest correction, and with this calculation, the largest one, I'm expecting the largest one should give me the closest. So this is the formulation. This is the implementation of the arc length method. Now let's take a look at the code and how this method behaves for this shallow truss problem. Now let's take a look at how this arc length method works. First, let's remember the problem that we are working on. This is our shallow truss. In that case, I will not use any springs to stabilize the system. So this length is 2500 and this length is 25, and we apply a load P here. And the analytical solution is as follows. We have a true snap true behavior. So it snaps and then it finds an equilibrium point somewhere here. Okay. Now the first thing that I will do is I will just solve it with the Newton-Raphson method. We discussed that. And when we look at the behavior, so I'm using 20 increments. So you start with the solution and very close to the limit point. Of course, you cannot catch these points because you have a fixed load vector. So at every step, you're increasing the force. So it increases the force, and the load deformation that you will see with the Newton-Raphson method is like that. So basically, if you use the Newton-Raphson method, you miss the limit point, you miss the unstable region, and you get a jump here and then catch a new equilibrium point. But we missed all what happens between these 2 points. Okay, so that's the deficiency of the Newton-Raphson method. Limit points and softening unstable regions cannot be solved. So that's why we have the arc length method. So I will discuss the implementation of it. So I have the stiffness of this truss, and this function calculates the internal force, and they all depend on the displacement. So I have a function here. So in this function, basically what I'm doing is I'm sending A1, A2, and A3 parameters. Remember that this is what we are trying to solve. A1 lambda square plus, let me rewrite it, A1 delta lambda squared plus A2 delta lambda plus A3 is equal to 0. So of course, depending on these values, you may not have a result, you may not have a root. And in that case, if we don't have a root, I'm just making these lambdas as equal to 0. So this algorithm is nothing but solution of a quadratic equation, and it gives me these 2 roots, okay, lambda 1 and lambda 2. Now we discussed that that's the which solution to choose. So I'm just sending the incremental lambdas that I calculated with the quadratic solver. So WP is equal to delta lambda 1. So this is WP. Delta V1 is delta V plus this value, delta lambda 1, this values. So I'm just calculating D1 for the delta lambda 1. I'm doing the same thing, the dot product 2 for delta lambda 2. And here I'm using the values from the previous iterations. And these are the newly calculated values depending on the values of delta lambda 1 and delta lambda 2. And then if the dot product is, the first dot product is larger than the second one, I'm choosing these 2 as my solution. Otherwise, the second root will give me the solution that I'm looking for. So this algorithm sends these to this subroutine sends these two results. So this is the main arc length method algorithm. So here we start with the increments. Of course, here the increments are not the load increments. They are the arc length increments, how many arc lengths that I will use. So I'll start with whatever the displacement that I have, calculate the tangent stiffness matrix. Total load divided by the tangent stiffness matrix give me the displacement. So with that, I'm again calculating A1, A2, and A3. The only difference is the iterative W and iterative lambda, they are all equal to 0. So I have a simpler equation here. So in the discussion, we said that what will happen if phi is equal to 0. We just ignore this. And the solution will be simply delta L over WPT. But here I also added these terms also. So I calculate A1, A2, A3 and solve for lambda. And then I'm checking the sign for lambda. So if the sign of lambda 1 is equal to the sign of the tangent stiffness matrix, so I'm just choosing these two or calculate these two by using the first root. If not, I'm using the second root. So I'm doing the initialization here. So I'm saying that this is my first predictor solution. These two represents the first predictor solutions. Okay. And I will use this to calculate the dot product. So I'm just adding these, saying that these are also my previous deltas. So I'm here calculating the total displacement and the total load factor. So now I start the iterations. The first iteration, calculate the tangent stiffness using the current displacement. Calculate the internal forces using the current displacement. Now the external force is the total lambda, whatever the load scale factor I have at this converge stage. And the predictor solution, I multiplied with P. Now from that I get the residual force. If the residual force is smaller than a particular value, I stop. This is the V hat, and this is the total. While calculating V hat, I'm using the residual. While calculating the total, I use the total force. And afterwards, again, we calculate the A1, A2, A3 coefficients. So here we have the full equation. Solve for lambda, and then we choose the correct root. Once we determine the correct root, I'm calculating the delta lambda, delta W for this iteration, updating the displacement and the total lambda, and this continues until we have convergence. Once it's done, the total displacement will be equal to beta, this one, and I'm also updating the lambda I. And the total force will be equal to lambda I plus P. Now our starting point will be taking a look at the spherical arc length method, meaning that this phi factor is equal to 0. So the arc length definition depends only the displacement. So the delta L here is equal to 5. I'm giving the total force to the algorithm. So this is the result. Now as you see, I was able to track the limit points and then the unstable region with this arc length method. These blue points shows the converged points for every increment. Now the next question is, okay, how the increments are determined, because when you look at it, the distances are not equally distributed. Actually they are. If you look at the projections, so displacement is equal to 5, this is 10, this is 15, this is 20. So basically what this algorithm is doing is, in terms of W, it draws a circle. So it draws an arc in such a way that it passes from 5. So every point we have W as equal to 5. Okay? And we make W equal to 5 and we are trying to find the corresponding load. So while determining the arc length, you can imagine, you can think about how much displacement you expect in a structure, okay, at a particular degrees of freedom, how many points you wanted, and this way you can determine your arc length or your increments. Okay, these are the points, so we were able to trace the full load deformation curve. Now the next question is, how many iterations do I need? In the spherical arc length method, we only need 2 iterations at every increment, which is also gives us a very fast convergence rate. Of course, here I'm comparing it with the BFGS method, with the Newton-Raphson method that we used previously. Now let's take a look at the cylindrical arc length method. In that case, our phi factor is equal to 1. Again, I'm using the same parameter, delta L is equal to 5, P is equal to 60. So when you look at these points, it looks like they all have some sort of a very similar distance in between in terms of arcs. So here the reason is, in our arc length definition, we are not only using the displacement, but we are also using some sort of the load increments as well. So for this specific problem, it gives almost more points when you compare it with the spherical arc length. So we again obtain the convergence. How many iterations? This time the iterations are a little bit larger, 3 to 4 iterations, but again we were able to trace the full load deformation curve. As a final step, let's take a look how the spherical and the cylindrical arc length method behave. Now the spherical, as we said before, these are all, it goes with constant displacement increments. These are all equal to 5. Okay, so basically if our maximum displacement is 6 divided by 5, we can have reached that point with 12 increments. But of course, in the cylindrical arc length method, we are using the forces as well to determine the length of the arc with certain scale factor, and it gives me more points. And in that case, we can say that this distance are very similar to each other, and it gives us more points. But in that case, I have to know how many points that I want, so that I can determine what should be my arc length and how many points that I want to trace the full load deformation curve. With this approach, we worked on the snap through behavior, but also you can catch the snapback behavior as well.